Hello everyone, today I'm excited to present our paper. Semantics lead the way, harmonizing semantic and texture modeling with asynchronous latent diffusion. As we know, latent diffusion models, LDMs, inherently follow a course-defined generation process, where semantic structure emerges slightly earlier than fine-grained texture, suggesting that preceding semantics can serve as a natural anchor for texture generation. As illustrated in this figure, at an early denoising stage, for example at t equals 0.2, the model mainly captures blurry, low-frequency structural information. Then, in later stages, it gradually sharpens the image and adds fine details. Recent studies enhance LDMs with discriminative semantic priors from pre-trained visual encoders, enabling faster convergence and improved generation quality. However, existing methods denoise semantic and texture latents synchronously, overlooking the natural generation ordering of diffusion. So we want to explicitly model this process by prioritizing semantic denoising first, then leveraging the formed semantics to guide texture denoising. This explicit ordering better aligns with the inherent generative mechanism of LDMs, simultaneously improving generation quality and training efficiency. We propose semantic-first diffusion, SFD, a novel latent diffusion paradigm that performs asynchronous denoising on semantic and texture latents, allowing semantics to denoise earlier and subsequently guide texture generation. We construct a joint semantic, texture representation in the latent space and build a three-stage asynchronous denoising pipeline on top of it. Specifically, S denotes the semantic latent, while Z represents the texture latent. During denoising, SFD operates in three phases. Stage I's semantic initialization, where semantic latents denoise first. Stage II, asynchronous generation, where semantics and textures denoise jointly but asynchronously, with semantics ahead of textures. Stage III, texture completion, where only textures continue refining. After denoising, only the texture latent is decoded for the final image. Next, let me walk you through the details of our method. For semantic modeling, we follow prior work and adopt features from a pre-trained vision foundation model, specifically DINOV2 base model, as our semantic representation. However, these raw dino features are high-dimensional and contain a certain level of redundancy. To address this, we design a transformer-based semantic VAE to compress the original dino features into a compact 16-channel semantic latent. This compression process preserves semantic information more effectively, providing a more complete and structured representation. The training objective is similar to a standard VAE, except that it reconstructs semantic features instead of pixel space. That is, both the input and output are VFM features, enabling efficient semantic compression. For texture modeling, we use the SDVAE to extract texture features. Since SDVAE is optimized for pixel-level reconstruction, it primarily captures low-level details and texture information. Finally, we concatenate the semantic latent and texture latent along the channel dimension to form our joint representation. During training, SFD assigns distinct time steps to semantics and textures. For each image, we first sample a semantic time step, T sub S, from an extended interval. Then, we derive the texture time step, T sub Z, by subtracting a fixed offset, delta T. After that, both time steps are clamped to the range from 0 to 1, and we ensure that T sub S is greater than or equal to T sub Z. This guarantees that the semantic latent is always less noisy than the texture latent, providing clearer structural guidance throughout denoising. The diffusion model adopts a transformer backbone that takes as input the noisy composite latent at different noise levels, 2 separate time steps, and the class label. It jointly predicts the velocities for semantic and texture components. The training objective combines velocity prediction losses for both semantic and texture latents. During inference, semantic-first diffusion performs denoising in 3 asynchronous phases: semantic initialization, asynchronous generation, and texture completion. The figure on the left shows that explicitly leading semantics ahead of textures, with a moderate temporal offset of delta t equals to 0.3, achieves an optimal balance between early semantic stabilization and subsequent texture collaboration. This effectively harmonizes the joint modeling of semantics and textures. From the results, we can see that the benefit of semantic-first guidance is quite significant. It not only improves the upper bound of generation quality, but also substantially accelerates training convergence. In particular, our method achieves a state-of-the-art FID score of 1.04 on ImageNet 256 times 256 generation. Moreover, it converges much faster, about 100 times faster than DI-T, and 33.3 times faster than Lightning DI-T. These tables compare SFD with other models. Next, we show some qualitative results. The figure on the left presents generation results at different training iterations, 160K, 320K, and 480K. Under the same random seed and identical initial noise, SFD is able to generate clearer structures and more realistic details even at early stages of training. This indicates a significantly faster convergence compared to other variants. The figure on the right demonstrates the separation between semantics and textures. In the first row, varying the semantic latent changes the global composition and layout of the image. In contrast, in the second row, we fix the semantic noise while varying the texture noise. As a result, the overall structure is preserved, while local appearance details, such as fur texture or scarf patterns, are modified. These results clearly show a clear separation between semantic and texture latent. Next, we present ablation studies. Table 3 shows that the semantic VAE and the semantic-first design are complementary and work synergistically, leading to consistent performance improvements. For semantic compression, we also explore alternative methods. As shown in Table 4, compared to PCA, the semantic VAE reduces the FID from 4.06 to 3.03. This demonstrates that the semantic VAE better preserves semantic integrity and spatial layout, providing a more stable and higher quality semantic prior for downstream generation. As a result, it plays a critical role in improving generation quality. Finally, in Table 5, we show that the semantic-first asynchronous diffusion strategy is also effective when applied to other frameworks that jointly model semantics and textures, such as ReDi. Next, we analyze the reconstruction performance. While recent work has highlighted the dilemma between reconstruction and generation in VAE, our SFD framework achieves state-of-the-art generation performance without sacrificing the reconstruction fidelity. Here we compare the reconstruction quality of latent space variants, VAVAE and RAE, SDVAE, which is adopted as the texture VAE in our method. SDVAE achieves the best reconstruction performance. This preservation of reconstruction quality makes SFD inherently more suitable for complex image synthesis tasks, such as text-to-image generation and consistency demanding image editing. Finally, to summarize, we propose semantic-first diffusion, SFD, a novel paradigm that performs asynchronous denoising on semantic and texture latents in latent diffusion models. By prioritizing semantic denoising to guide texture refinement, SFD achieves faster convergence and superior generation quality. Extensive experiments on ImageNet class-conditional generation demonstrate that SFD consistently outperforms competing methods. Our findings suggest that controlling the relative denoising pace between semantics and textures is crucial for efficient generative modeling, establishing representation-level asynchronous denoising as a promising direction for future diffusion research.